Good morning from here in London. Thank you for joining us for today's aerospace webinar. Today we'll be looking at using multi-physics simulation to reduce airport noise challenges. Okay, we're delighted to have two speakers for you. Our first speaker is Darrell Rittenberg. Darrell is the aerospace and defense industry segment leader for STAR CCM Plus as part of the Simcenter portfolio. Over the past 17 years, Darrell has helped engineering organizations leverage CFD and other computational methods to drive innovation in their design process. As aerospace and defense industry segment leader for STAR CCM Plus, Darrell worked with aerospace and defense customers around the world to tackle engineering design problems once the domain of costly design, test, fail, repeat methods. Darrell received his PhD in chemical physics from the University of Utah, where he studied design modeling and characterization of advanced materials. He studied at Osaka University as a Monbusho Fellow and as a postdoctoral fellow at the University of Washington. He is currently a senior member of the AIAA and a number of the Inlets, Nozzles, and Propulsion Systems Integration Technical Committee. We're also delighted to welcome Parthiv N. Shah, PhD. Parthiv is a senior technical advisor at ATA Engineering, Inc., based in San Diego, California. Over the last decade at ATA, he has worked on many projects in fluid dynamics, aeroacoustics, propulsion, turbomachinery, and has been the principal investigator on a number of small business innovation research projects. Prior to ATA, he also worked for around 5 years at Pratt & Whitney in Connecticut in diverse disciplines related to aircraft engines. He holds a BS in aerospace engineering from the University of Virginia, an MS in mechanical and aerospace engineering from Rutgers, and a PhD in mechanical engineering from MIT. Okay, so without further ado, I'm going to hand things over to our first speaker today, Darrell Rittenberg.
Well, good morning, everyone. It's nice to have an opportunity to discuss an area of prime interest in the aerospace industry today, which is how can we leverage multi-physics CFD simulation to reduce airport noise. And this presentation is in two parts, so I will go through a quick introduction to the subject, some of the current research that's being done, and a quick introduction to STAR CCM Plus for aeroacoustic simulation. And then the balance of our discussion will be with Parthiv, who will actually go through some work that they've done at ATA Engineering on a novel air brake system. And we should have plenty of time for Q&A. And so with that, I wanted to set the stage, so to speak, and talk about what it is that we at Siemens PL really focused on. What are we trying to do with our technology? And we see the industry as changing perhaps more now than at any other time in our history. And there's a lot of new innovations and disruptive technologies that are coming down the pipeline. Our goal is to work with organizations to bring technology to help them be more innovative. And we want those technologies to truly improve what's being done from an engineering perspective. Elon Musk, I think, said it well when he said any company that says stationary with their technology will be exceeded by their competitors. And this is probably no more true in history than today. In fact, I heard a statistic recently that close to 25% of the Fortune 500 from a decade ago, those companies are actually out of business. So that just shows you that there's a lot of potential for these disruptive technologies. Our goal is to make sure that you have the right tools to address that. And so one of those tools is STAR CCM Plus. I'm not going to spend a tremendous amount of time talking about the tool. Most of you may be aware of the type of work we do, but CCM Plus is really a fluid dynamics code, but we have added multi-physics to this over the years, and now we can actually address a number of different engineering challenges ranging from simple fluid dynamics, but we're going to focus on aeroacoustics. But that's really just one aspect of what can be done with STAR CCM Plus. So we want to focus first on how can STAR CCM Plus be used so that you can leverage the fluid dynamics to understand acoustic characterization of a geometry. So what's driving some of these trends in noise reduction. And, well, it's actually, and I'll talk about this in detail, there's been tremendous changes in just populations being near to urban airports. I have a good friend who lives by SeaTac International Airport, which is about 10 kilometers from my house. And about 4 years ago, went over to his house for a barbecue, and boy, it was really loud because he's actually in one of the flight paths. He said, yeah, we're working on it. There's going to be some changes. I was there last summer, and he's right. It's amazing the amount of difference that's been in terms of the planning and the noise abatement strategies. It's actually somewhat pleasant to go visit him now. And that's because there's been a lot of research into aircraft noise. And now this is from ICAO, which is the International Civil Aviation Organization, which is a UN organization. And they've said that aircraft noise is the most significant cause of adverse community reaction related to operation and expansion of airports. And this is going to be expected to remain the case for the region of the world for the foreseeable future. And that's right, it's not going to change. So what are we doing about it as an industry? Well, there's been some improvement in the noise level restrictions. And so the current plan is actually the Chapter 14, that's the CAEP 9, which came into effect in 2013, which is likely one of the reasons why there was such a significant decrease in noise at my friend's house who's over by SeaTac. But if we look at some of the work that's being done in the industry by Akari, they are actually looking at strategies to reduce overall aircraft noise by 65% over the next 20 years. That's an amazing amount of improvement from where we are today, but there's lots of viable reasons to do that. Number one, there's been a tremendous growth in population around these urban airports. So we have these two competing demands. We have the demand for convenient air travel. Air travel has been growing exponentially, and it's going to continue to grow exponentially for the foreseeable future, which means we have more aircraft wanting to come in and out of these population centers, which means that you have this interface then between people who live near an airport and the airport operation. But there's a good reason to do that in that if you look at SNA, which is the John Wayne International Airport, which is in Santa Ana, California, they are basically able to account for close to 4,000 jobs that are brought into that community from the airport. So we have stricter regulations on one side, we have growth of these suburban airports, and we know that there's some balance in balance. You have growth in the economy. How does all this play together? Well, this is basically an approach that's been adopted by ICAO, which is a balanced approach which takes into account 4 areas. First is land use and planning, not always appropriate, especially with urban sprawl. Sometimes you can avoid putting people in flight paths, but not always, and so you have to look for other strategies. Operational restrictions, certainly we've seen in terms of when planes will fly in and out of major airports, there's been a decrease in flights in sleeping hours. Of course, we have noise abatement strategies. This includes repositioning where we have runways as well as novel enclosures to reduce engine noise on takeoff. But what we're going to talk about specifically is going to be reducing noise at the source. In effect, how can we reduce noise through effectively looking at the aircraft itself, and that includes both the approach with Partheeth will actually talk about this in great detail, as well as noise from the actual aerostructure. And so we'll talk about that as well. So let's dive into that. From a STAR CCM Plus perspective, really from an aeroacoustic simulation perspective, we can actually look at broadband noise, midfield prediction, as well as FWH surface integrals, as well as partnering with tools like SysNoise and Actran. So there's a lot of acoustics that can be done with the tool. One good example is some work we did as part of the Aeroacoustic Prediction Workshop. This was actually done in conjunction with Mohamed Tabesh at Bombardier Aerospace in Montreal. And the idea was to take a known geometry in full fidelity without removing any of the geometric complexity and use CFD to predict the acoustic signature as well as the point source of noise. Where is the noise coming from in the geometry? And the secondary objective was to make sure that this work could be done in as short a delta T in terms of time on the wall clock as possible. And the key here is that to make changes to a design, you have to be able to understand what those changes do to the performance of the geometry in 1 or 2 days. If you're trying to do this and it's taking months, it really can't affect design. So one thing Dr. Debesh said was that using high fidelity CAD model in STAR CCM Plus, they were able to predict the source of landing gear noise. And as I'll show you here in a moment, actually able to do that with in this case, just a couple of days. So let's quickly talk about that in detail. So we, again, started with full CAD geometry. We did not do any simplification. We wanted to take as high a fidelity CAD model as possible into our code. We used a trim cell mesh, which is fine if you happen to have flow aligned with the domain. We used a density-based coupled solver, and this was a DES solution. We ran this on 256 cores, and it took nominally 48 hours per configuration. So frankly, that's in that 2-day period. That's enough for design decisions. So in terms of the results, so we actually looked at the acoustic results from NASA Glenn. So this is actually looking for the sources of noise on the geometry. And as you can see, we can map those to the geometric complexity on our CAD model, which was in good agreement. So we actually were able to show that the geometric sources of noise on the landing gear agree quite well with experiment. But that's only half the story. The other is, of course, the acoustic response. So we looked at 2 points on the geometry. First was actually part of the leading bit of the assembly off of one of the geometric components. And secondarily, we looked at the trailing edge of the wheel assembly itself. So if we look first at the 1,000 hertz response from the first point of interest, you can see that, in fact, the black line being experiment and the blue line is from STAR CCM Plus. We are actually very close in terms of the overall acoustic response in that area. We can actually then look at the area around the wheel itself. In this case, we were, I would say within error, but perhaps not as strong a match as we were in the first point. But nevertheless, according to Debesh and others, this was pretty consistent with what other codes were projecting. Again, our goal was to try to do this in a 48-hour period. Okay, but we're really only talking about now some landing gear noise, and that's not enough because, in fact, if you look at the acoustics of an airplane during the descent process, you actually have quite a bit of noise being generated by aerodynamic surfaces and air brake surfaces. And what does that mean? Well, it means that when you're using computational methods, you really have to look at both aerodynamic performance as well as the acoustics and make sure that you have good agreement on both. And thankfully, with STAR CCM Plus, you can see we've actually done work in this area, and we actually can show quite good agreement in terms of the air performance compared to the wind tunnel data as well as the acoustics. So which is a good way to transition to some work done by our Partith and his group at ATA. And so Partith is going to be talking about using simulation and the technology maturation of an engine air brake system from aerodynamic concept all the way through to full-scale demonstration.
Thank you, Jay and Darrell. My name is Partith Shah, and I work at ATA Engineering at our headquarters in San Diego. And I work with and lead a team of fluids and CFD engineers located here in San Diego and in a number of our regional offices in the United States. I'm looking forward to presenting the story of our recent engine air brake technology demonstrator that's pictured on this slide. I'd like to begin with an agenda of today's webinar. I'll first start with a quick slide to tell you a bit more about our company, ATA Engineering. And then I'll go into a motivation of this project, which focuses on enabling new ways to reduce the noise impact of aircraft on descent and approach. Then I'll give a brief background on how the engine air brake was conceived as part of a collaborative university project aimed at noise reduction. And then I'll go into the details of how we matured the technology through a pair of Phase 1 and Phase 2 NASA-sponsored small business innovation research projects. And I'll also try to highlight the role of simulation in this effort. Finally, I'll conclude and I'll give an outlook of our future goals. So ATA Engineering is an engineering services company. We're headquartered in San Diego, California, and we've existed for 17 years, but our senior management has been together for over 35. And during this time, we provided test and analysis-driven design solutions for structural, mechanical, thermal, and fluid systems. We are an employee-owned small business, and we have over 100 degreed engineers at 7 locations around the country. And we're also a VAR, a value-added reseller of Siemens PLM software products. We specialize in the areas of design and analysis, and that includes implementation, support, and training for those tools. Our CFT team has been using STAR CCM Plus as a flow solver for about a decade now on fluids engineering projects in many industries, including aerospace and defense, entertainment, electronics, consumer products, among others. And as a small business, we also do R&D and methods development through small business innovation research projects sponsored by U.S. government agencies. So the topic of this webinar gives an example of the outcomes of one such R&D project. So I'll next go into some motivation. I'll begin with identifying the problem, which is how do we reduce the sound footprint of aircraft on descent and approach? As you see in the photograph, airports are often located near population centers, and air travel is growing. So populations are at risk of greater exposure unless noise mitigation strategies are in place. Now, on approach, the noise from the system, that is the airframe and its propulsor, is typically dominated by the airframe and not the engines. And key sources include the undercarriage, the flaps, and other control surfaces and their edges, which are interacting with turbulent flow in general. And these sources scale typically with the 5th or 6th power of the velocity of the aircraft. And so in order to mitigate noise, people have conceived of different approaches, such as flying slower. That would reduce the acoustic source strength, but it would require a high lift coefficient on approach. Flying steeper, that is putting the sources farther away from the community, that would require a low lift-to-drag ratio, or flying cleaner, that is to remove some of the exposed structures during the descent. And all of that motivates a need for what I call quiet drag. Now, a typical approach glide slope for an aircraft is about 3 degrees. And so if we were to focus on the steep approach for a minute, if we could get a device that would give us quiet drag at a constant approach speed to take that up to, say, 4 degrees, 1 degree more, we'd expect to see about 2.5 decibels noise reduction on the ground, just by putting the sources farther from the community. And if we were to go from 3 to 6 degrees, that would be about 6 dB. It turns out for a turbofan-powered aircraft, scaling from small business jets out to large commercial aircraft, if you want to go about a degree steeper, you need about the same drag as a bluff body with the area cross-section of your propulsion system, or about a little bit less than 2% of your landing weight. If you want to go 3 degrees steeper, you need 3 times that drag. And it's also worth noting that if we are looking for drag, then any residual thrust that our engines are producing are kind of opposing our objectives. So the next part of the motivation is just to explain, to show you some examples of how it's done today. And I'm going to use London City Airport as an example where a steep descent and approach is mandated due to the location of the airport being very close to the city center. And the slide shows 2 different approaches that were certified on 2 different aircraft. Both of them were fairly unique. So the first example is the BAE 146, which was in production from 1978 to 2001. Their technical solution was this 2-pedal air brake below the tail rudder. And it was basically a large structure that would deploy in order to generate additional airframe drag. And clearly, as you could see, there could be a trade-off between the weight and complexity of a device like that versus the competitive advantage of access to a specific airport. A more modern example is the A318. This was marketed later as a replacement for the BAE 146 for London City. And today, British Airways flies this in an all-business class service between JFK and London City, so it's certainly a very lucrative route. Their technical solution, however, required increasing the engine power to reduce the go-around spool-up time, and coming in much dirtier. They had to put in full flaps and flats, and they were putting in speed brakes. So they had high lift devices and lift-killing devices combined to generate drag, and because they had to do this, they had to increase their approach speed a little bit from the reduced lift. And some articles have suggested that the landings can sometimes be a little firmer than ideal. And so that kind of motivates the topic of the device we're looking at, called an engine air brake, which is meant to generate drag via thrust reduction. And that would potentially allow the resetting of some of these aerodynamic surfaces for slower, steeper, or cleaner flight. So as I noted, the engines are powered, and so the desired drag is always countered by any residual thrust that we're making. Ideally, we could just shut off the engines and glide in, and that would be great for noise. But for safety, we can't do that because we have to be able to get to full power in the event of a go-around. So this slide introduces what's new with our approach. That is the idea behind the engine air brake. What the device does is it exploits the strong radial pressure gradient that would be associated with normally a steady swirling flow. And the low pressure in the core of the swirling exhaust would give you pressure drag. It's intended to be a deployable drag management device with vanes that penetrate in radially from the nozzle cowl, and they simultaneously swirl the exhaust and they carefully regulate the flow capacity of the nozzle. And it's meant to be an enabling technology for slower, steeper, or acoustically cleaner approaches when you cannot further reduce the thrust of your engine. Okay, so that's a little bit of motivation. I'd like to quickly give one or two charts on the background of this topic before I go into how we've matured this technology through simulation. So I borrowed a slide from charts related to my PhD research, and back in the 2006 timeframe, I was fortunate enough to participate in a multi-university, multidisciplinary collaboration called the Silent Aircraft Initiative. And as the slide shows, that research effort involved many dozens of researchers at MIT and Cambridge, and the goal of the project would be to define what a functionally silent aircraft would look like, something that would be functionally inaudible around the perimeter of an airplane. And the outcome was a hybrid wing-body aircraft that's pictured here. And at that time, the need for quiet drag was identified as a potential low-noise enabler to an aircraft that would be quite slippery on descent and approach. We called that idea an engine air brake, though at the time we hadn't quite envisioned how we would be able to integrate that with an engine. But as part of that work, we came up with the idea of swirling the exhaust flow. And since engine integration would be quite complex, in my PhD work, which was sponsored by NASA, we demonstrated the idea that a steady exhaust flow emanating from a nacelle with swirl could potentially give quiet drag. And the simplest implementation of that was what we call the Swirl Tube, which was a ram pressure-driven nacelle pictured on the upper right, which we demonstrated and tested in the MIT Wright Brothers wind tunnel. And we showed that we could get bluff body-like drag without bluff body-like separation. The concept was then later tested at NASA Langley's Quiet Flow facility, where we verified that there was a sweet spot where you could get fairly high drag but still achieve low noise. And the threshold for that was set by a phenomenon called vortex breakdown. However, since ram air nacelles don't magically appear on aircraft on demand, one of the major conclusions I took away from this work was that the logical next step would be to work on how we could integrate this into an engine. And so that leads me into the discussion of our technology maturation. Along the way, I'll focus on how we use simulation to answer increasingly complex and multidisciplinary questions. So I joined ATA in 2007, about a year after my PhD, and we had an SBIR project that started in 2008 from NASA to explore how we could mature the technology readiness level. So one of the first concepts that we explored was whether the swirl that we could put in the flow from the rotor of the fan could be passed through the engine in a drag generation mode. And this idea led us to a set of variable geometry exit guide vanes that would unload themselves when a drag boost was needed. So in the first phase of this project, ATA used STAR CCM to simulate that flow on a NASA turbofan engine geometry. This is the flow that you see pictured would be the conventional or the baseline setup, and we explored whether a variable geometry exit guide vane could then be allowed to pass a swirling flow. And we demonstrated that there was potential for this type of a concept, and in the phase 2 of the project we wanted to simulate such fan-driven high bypass swirling exhaust flows on real hardware. So we decided we would focus on blown nozzle testing. And so here's an example of some STAR CCM simulations we did in the second phase of that work, where the hardware was a stationary set of swirl vanes located in the bypass stream of a two-stream nozzle. And the goal of those simulations was to predict the relationship between the flow capacity, the swirl angle, and the equivalent drag. And later, we tested their noise in a NASA facility to get the full picture of how these devices could potentially be used at a system level. Now, one of the things we recognized in that second phase also was that there's many different types of engine architectures and pylon architectures. If you look at the back of an aircraft, you'll see that. And specifically, many of them are either separate flow or mixed flow exhausts. For separate flow engines, we had one challenge, which was that the duct is typically bifurcated by a large pylon structure that holds the engine onto the airframe. And that would, in general, inhibit the device from passing a single axisymmetric swirling flow. So another concept that we explored involved having a swirling exhaust created by, at the nozzle exit by a stationary set of swirl vanes along with a pylon that had a trailing edge that could deflect to assist swirling that flow. And so here's another example of a STAR CCM plus simulation where we tested a more advanced concept. In the later part of this project, we were fortunate enough to test these designs at NASA's Aeroacoustic Propulsion Laboratory at Glenn Research Center in Cleveland, Ohio. And here you see a picture of that facility. You see an anechoic hemispherical dome building. And you can also see pictures of a lot of the hardware that we developed, which took advantage of things like rapid prototyping to achieve the unique geometries that we were simulating using CFD. And so finally, since we measured the noise, we applied all of those results, the flow capacity, the drag, the swirl angle, and the noise, to a flyover simulation. And so this is an example of what we found. So the x-axis you see on this chart is a time variable, which represents the time that is elapsing during the overflight of an aircraft. And the y-axis would be an integrated noise metric. So one of the things we found was that unlike a ram air-driven swirling exhaust flow, which was exceedingly quiet, the jet noise from a fan-driven swirling flow would actually increase. And so what you see here is that the jet noise component alone from the baseline would increase. Well, that is the black relative to the blue. So we assessed, or we applied a penalty to our simulation to show this. However, the overall system noise could be reduced, and that was because we could use this drag generated by the swirling flow to go from a 3.2 to a 4.4 degree glide slope angle at constant speed without changing the aerodynamics or the self noise of any of the other sources. And the reason for this was because all of the other sources dominated at this condition and were not, the jet noise was very much masked by the airframe noise. And so from this we came away with a few takeaways. The first was that our engine air brake is not a jet noise reduction device. However, it is potentially a system noise reduction device. And the preferred design that you have to come up with would be tied to the relationship between the relative sound sources that are on the system. That is the jet noise, the engine, and then all the airframe sources. So this was very encouraging. And in a second SBIR project sponsored by NASA, we came up with the discovery of how we could integrate this into a mixed flow exhaust engine. And so the next and most challenging objective then became, how do we demonstrate this on a real engine? We were lucky enough to find an engine partner, Williams International, and they're located in Walled Lake, Michigan, and they make medium bypass ratio engines for the smaller business jet sector. And we were able to conceive of this follow-on project where the EAB would be demonstrated on their FJ44-4 engine. You can see some of the specifications of the engine here, and an example of one of the aircraft it powers is shown in the upper right picture. That's the Cessna CJ4. So having an engine partner on board allowed us to establish more rigorous design requirements and ground us in reality. And so this slide kind of talks through some of the very complex and competing requirements that spanned multiple disciplines. So a key feature of the engine air brake is that a significant fraction of the suction side of the vane would be wetted by the external flow when stowed, i.e. the vane has a surface that would normally be defined by the aircraft engine's external cowl. And when the vanes deploy, they actually open up a cutout, which allows the nozzle to regulate the exit area. So for aerodynamic performance, with this type of a design approach, our goal was to demonstrate that we could reduce the thrust without changing the engine's rotational speed by 15%, and that would enable a 1 to a 1.5 degree glide slope increase, with all other things being kept the same. But we also had to demonstrate operability, that is, margin relative to the surge limits of the engine. So when we were stowed, we wanted to demonstrate that there was no change in performance, and when we were partially deployed, we wanted to demonstrate that we had adequate surge margin, and when we were fully deployed, we actually wanted to demonstrate that we had slightly open exit area. Additionally, as a mechanical system, we wanted to show that deployment time would be less than 5 seconds. The stow time would be less than half a second to be able to do go-around, and that we could package the entire mechanism within a notional engine flight cowl. And then we would also want to be able to return to the stowed position if our hydraulic pressure was lost. From a structural point of view, we had to make sure that we had strength for high cycle fatigue. We designed to the right natural frequencies and stiffness, and we selected materials that could withstand the thermal environment of this mixed flow hot and cold exhaust. And finally, from an acoustics point of view, we wanted to make sure that we did not have any rogue tones or separations that would contaminate the noise due to the device itself. And we were shooting for at least 1 decibel of demonstrable noise reduction when on a system level basis. So I'm going to now go through a few of the examples of some of the simulation and some of the design process, just because I think it's interesting. So on the CAD side, we had the challenge of creating the right geometry so that we'd have a smooth inner surface, which would be, when stowed, would have no gaps. And here's an example of some of the early sketches our designers made, where they were trying to figure out how to do the Boolean operations to ensure that this vane would be able to integrate with the nozzle as a mechanism. Because we use Siemens tools, we used parametric solid modeling to rapidly generate different designs with varying parameters. And so we would use NX to create the CAD bodies for the CFD, and then we'd use the CFD results to update our parameters and iterate on the NX design. And in general, the designers found that a little bit more effort in the beginning in building initial models made it more robust going forward. Here are some of the design parameters that we studied with CFD. So that included the vane count, the swirl angle, the rotation angle for deployment, the chord length of the vanes, and how much cutout area relief depth we wanted. And within NX, we used expressions to govern the different parameters in the model. So you can just see an example of some of the expressions which cover the sketch of our airfoils, the number of vanes, the rotation, the swirl angle, etc. On the CFD side in STAR CCM Plus, we generated the CFD volumes in NX, and then we brought them into STAR CCM, and we took advantage of some of the turbomachinery analysis paradigms, such as mixing planes. And these were especially useful because the engine had a lobed mixer, which had a different periodicity than our swirl vanes. But by doing this and solving the simulation in a wedge, we were able to use the volume more efficiently in terms of mesh resolution, and we were able to get more accurate results. I have one slide here that kind of summarizes the many aerodynamic and structural simulations that were required in order to complete the design. So in STAR CCM Plus, we used RAN CFD for performance. We also used RAN CFD for gap leakage analysis. There was also some multi-physics in the form of conjugate heat transfer, where we had the flow over the vanes, and then we had a solid mesh of the vanes to determine what the temperature profile in our vanes would be. We used large eddy simulation for assessing what the unsteady loads could be. And we also did some flutter assessment to make sure that the vanes would not find an unstable operating condition. On the structural side, using NX, we also did FEA in terms of static stress, modal analysis, random and sign analysis. We did fatigue analysis, and we also did analysis for thermal and structural deformations. And of course, there were many hand calculations that the designers had to do. So this was really an analysis-driven design. Finally, we also had to design a deployment mechanism. And here is an early sketch from our design team of how the vanes could be deployed. We learned early that the swirl angle of the vanes would make it tricky to connect our linkages. And so we used NX simulation tools to also verify that that would properly work. Here's an example of a solid model with assembly constraints in it, which showed us how our parts would really interact when we put the whole mechanism together. And here's another example of that, kind of zoomed in on our actuator ring. And this also helped us check the interference between our parts, because we had very many parts placed closely together in the mechanism. So finally, after we completed the design, we had vendors machine our piece parts, and we assembled the mechanism in our design studio here in San Diego. And I'd like to show you a video of our bench level deployment. What you're going to see is the engine air brake deploying and then stowing very quickly. So I'm going to hit play. So as you can see, we've got these single acting rams which get hydraulic pressure. They rotate a ring. That rotates the vane shafts via a lever arm, which is connected to an adjustable linkage. And those vanes are acting against a spring, and that spring was there as a safety feature so that if hydraulic power was lost, these vanes would return to the stowed position. And generally in operation, the spring is greatly assisted by the engine's aerodynamics as well, which want to force these vanes to close. So moving on, we took our nozzle out to Williams International's outdoor test facility in Walled Lake, Michigan for the ground test demonstration. And one of the things we first did is map out the performance of the engine air brake as a function of the vane rotation angle, using position locks to hold each angle into place. And the plot on the right shows on the x-axis a dimensionless flow capacity, and on the y-axis the drag. And it shows it for various levels of deployment. So it goes everywhere from stowed, where we have full flow capacity and no additional drag, out to partially deployed, where we lose flow capacity, and then out to fully deployed, where we gain flow capacity and we have the most drag that we're making due to the swirling flow. What this also shows is that there's measurements and CFD shown, and it shows that the CFD did a pretty good job of helping us figure out what our pinch points would be. Additionally, we designed the nozzle for a higher nozzle exit flow so that we could actually predict and demonstrate a slightly reduced fuel burn when the device is fully deployed. So now I'm going to play another video for you. It's got some audio along with it, and it's going to show the dynamic deployment and stowing of the device on the test stand in Michigan. There's audio, so you hear the broadband noise signature of the jet noise shifting in frequency, and what you're going to see is the device deploying rather slowly, about 15 or 20 seconds into the movie, and then you'll see a very quick stowing of the device towards the end of the movie, so don't blink towards the end. Finally, we also measured the noise with an array of microphones placed on an arc on the ground in that test facility. And what we saw was, while there was a modest noise increase due to the swirling jet exhaust, when we put this in a steep approach simulation, we did verify that, or predict that we would potentially get 1 to 3 dB noise reduction potential by allowing the aircraft to fly at a steeper approach angle while keeping the aerodynamics fixed. And so that kind of concludes the overall story of this project. I just wanted to leave with a few key messages. First, an engine air brake is a device that would provide aircraft drag management via thrust reduction. And the idea is to take advantage of the fact that swirling flows have low pressures in their cores. So you get equivalently what we'd call pressure drag. And I'd like to leave you with the idea that it would be potentially an enabling technology for slower, steeper, or acoustically cleaner approaches or descents when engine thrust can't further be reduced. And finally, in our full-scale prototype demonstration, we were able to show that we could get equivalent drag in the form of 15% thrust reduction at high power, a so-called dirty approach, that our operability margins were okay across all the deployment angles, that we demonstrated a dynamic deployment of less than half a second and a very rapid stow of, a dynamic deployment of 5 seconds and a very rapid stow of less than half a second, which would be suitable for go-around. The entire mechanism would fit within a notional cowl, and that we expect that a typical steep approach glide slope potential might be 1 to 1.5 degrees greater with a noise reduction potential of 1 to 3 1 to 3 decibels. Finally, I'll leave you with an outlook. So in this webinar, I kind of gave you a technology development roadmap that we've been on, where there's a blue axis here that's TRL, Technology Readiness Level, as defined by NASA. 1 would be something like a napkin sketch, and 9 would be something that would be ready for commercial use. We tend to think of ourselves at around the level of 6, and these boxes kind of show the chronological advancement of the technology. And so where we would like to go with this eventually is a flight test demonstration showing that quiet, steep approaches can actually be made utilizing a device such as this one. Finally, I'll leave you with some research I did going way back, 1942, from the Ministry of Supply in the UK, this report on a resume of aerodynamic data on air brakes. And this says, in designing air brakes, the aim should be to produce the required drag with as far as possible no other effects in the airplane. And that's really what we're going for with this kind of a device. So finally, I'd like to end with some acknowledgements. The SBIR contracts were monitored by Dr. Chris Miller at NASA, who was a very great source of help and support. And I wanted to acknowledge the very talented team members, both at Williams International and at ATA Engineering, without whom this work would not have been possible. So that ends my talk, and I will be open to any questions. Thank you.
With that, the session is closed. Goodbye.